Okay, Assalamualaikum dan salam sejahtera. So, pada hari ini, okay, English kan? Sudah lupa pula. Banyaklah kelas hari ni. Assalamualaikum and good afternoon. Today, we will discuss about the graph of a specific energy. Previously, we already discussed about how to draw the specific energy, which contain the static energy and also the kinetic energy. So for static energy, we could plot it using Excel graph because the equation is very simple. The static energy is equal to Y, so we could plot as this one. So means that the energy, the value of Y is equal to the energy of the static energy. However, for kinetic energy, we need to calculate using this equation. Okay, this part is explained about the kinetic energy, and you need to use the idea of specific discharge as shown here. So you could get this from my previous lecture video. So and then if we draw this one, we found that this kinetic energy will curve like this. Okay, I'm sorry. The kinetic energy will curve like this. So and then if we want to draw the total curve of the specific energy, we need to draw like this. Okay, so the idea of drawing the specific energy curve here is, first, for example, if you have x-axis and y-axis here, so and then you need to draw the static energy, which is the straight line there. So and then you need to draw the kinetic energy curve. So it's something like this. So and then the total curve or the total pattern of the specific energy will lay on this region. Okay, so this is the rule to draw the specific energy curve. So it must only occur at this region. Okay, so if we see this graph, for example, we have this graph, we will find that at one point here, so it only occur when the critical depth at YC here. So mean there is only one amount of YC that will give us this value. And this value is the minimum value of energy, of the specific energy. And because of that, we call this point as critical depth. Okay, why we call this point as critical depth? So it is because from this moment, after this, the increment of energy will be exponential. So mean it will be increased rapidly. Okay, however, at this direction, the increment energy was occur, but the energy increment is not so rapid. Okay, so and then at this point, for example, we take these 2 points. So we have this point and we have this point. So at this point, we found that, okay, in these 2 points, it's occur at 2 different value. So at y1 and also at y2. However, these 2 value will give you a same specific energy. That's why we call these 2 points as alternate depth. Okay, so and then for the alternate depth here, actually you need to know if you get 1 point here and that point is not a critical depth, so means that there must be another point that give you the same amount of energy. So normally in my question, I will ask you to find what is that another point. So and then the reason of this one is we need to determine, or we need to predict the hydraulic jump based on the location of the critical depth. Because if your flow is going to this direction, okay, so means that after it go through critical depth, so mean the hydraulic jump will occur. Mean the possibility of hydraulic jump to occur is much higher compared to the fluid that still lay at this region. So that's why in open channel flow, the calculation of the critical depth is very critical, because it is the turning point where the hydraulic jump occur or not. Okay, this is the idea of the graph. Okay, you could read. So I just read and show you the critical ideas of this one. So number one, the diagram applies for a given cross-section and discharge. As the depth of flow increase, the static energy increases and kinetic energy decreases. So the total energy curve approach the static energy curve for high depth and the kinetic energy curve for small depth. Okay, you could see the graph later on. The specific energy is minimum, E min, for a particular depth. This depth happens to be the critical depth for which the Froude number is equal to 1.0. So here, the important point that you should know is at critical depth here, so the Froude number is equal to 1.0. Later on in tutorial, we will see about this situation. Okay, so energy minimum is the only energy value with a singular depth. This is what I said just now. We only have 1 point for critical point, so mean there is only one amount of energy, and there is only one amount of the depth. Okay, depth less than critical depth, we call it as supercritical because the Froude number is larger than 1. So the depth less than critical depth, so means that the depth which is less than the critical depth, so means at this area. So at that area, the Froude number is larger than 1.0. So, and then the depth greater than the critical depth, we call it as subcritical flow. So means that for the depth from here and above, we call it as a subcritical, means below critical condition. Okay, and then the Froude number is less than 1.0 here. The Froude number is larger than 1.0, and at critical depth here, the Froude number is equal to 1.0. Okay. So, and then for all other energy value, there are two depths associated, one greater than the critical depth and one less than the critical depth. The two depths associated with the same energy value are referred to as alternate depth. So this is the definition of the alternate depths. As discharge increase, the specific energy curve moves to the upper right portion of the chart. So means that if the flow rate is increased, so means the thickness or the depth is become higher and higher. So it will move to the upper right portion. So mean the upper right portion is here. Okay. Okay, so this is if we have a few flow rate, for example. So the curve will become like this. So this is the value of Q. This is the value of Q1, and this is value of Q2, which is the Q2 is the highest flow rate in this situation. So we found that the curve is moving upward like this one. And this region, if we plot it like this one, we found that this region is subcritical region, which the Froude number here is less than 1. However, the region here is called as supercritical because the Froude number is larger than 1, and the hydraulic jump can occur at this situation. So normally it's the possibility to occur is very high. Okay, now we come to the question, okay, how to determine the alternate depth in this situation. Okay, let's say we have the energy equation here. So the E is equal to Q square over 2gy square, because we already replaced this with the specific flow rate. So, and then there is a minimum value of E at a certain value of y called the critical depth. So how to calculate this one? We know previously in our secondary school or high school, if we have a quadratic graph like this, so if we want to calculate what is the maximum point here, so we will do the idea of dy dx. Okay, and then we equal to 0, so we get the maximum point. So same goes to this idea. So we doing the differential, so we use the dE over dy. So and then we say that dE over dy is equal to 0. So we do the differential for this term. So dE dy equal to 0, so we get this term. So from this calculation, we could find that the E minimum occurs at yc by this equation. So we could find it is equal to q square over g with a power of 1 over 3. So, or you could calculate by using the flow rate like this one. So I hope you could remember this equation, or you could do the derivation, a very simple derivation as shown in this slide. So, and then the idea of minimum energy, okay, according to the experimental verification and so on. So we could find that the location of energy minimum is actually 3 over 2 yc. So this is the location where the critical location is. So and then, so the depth yc, y critical, correspond to channel velocity equal to the shallow water wave propagation speed c0. Okay, so and then because we assume that the Froude number is equal to 1, so here we could have the calculation like this one. So we have V here, so and then V here we substitute with the idea of this one. So we have the Q square over y square. So and then, okay, and then we substitute it here. So and then we substitute the value of Froude number is equal to 1. Then we could have these terms. So and then, so this is just the idea again about the subcritical and supercritical. So if the value of the Froude at critical level, so the Froude number is equal to 1. So and then if the value, the V is less than Vc here, so we call it as subcritical, and if the velocity is larger than V critical, so we call it at supercritical. So this is just a note. So the idea is the same that I explained to you before this. Okay, so this is another explanation or another graph showing the region of subcritical and supercritical here. Okay, so we comes to the how to calculate the alternate depth. Okay, we know from the equation, so the y critical here is 0.971. So we know that the height here is 0.971 as we calculate according to the equation here. So and then we could calculate the minimum specific energy by substituting the value of yc here. So and then we get the E minimum is equal to 1.457 meter. So here, please be careful. Please make some revision from Fluid Mechanics 1 and Fluid Mechanics 2. 1.457 meter is reflected the energy here. So means that it's same with the Bernoulli equation. In Bernoulli equation, we are using meter to express energy. So the idea is, okay, if people say that, okay, the energy head, okay, is 1.457 meters, so means that that energy could lift water until 1.457 meters. Because normally, maybe some of you already forgot about fluid mechanics 1 and 2. So people start to think that energy should be measured in joules. Oh, that is correct. But in this situation, we reflect the energy in terms of the capability of the energy to lift water until certain height. So that's why we use the units for the energy here is in meter. So I hope you could revise your fluid 1 and fluid 2 knowledge about this. So the very simple one is you just assume that the minimum energy can lift water until 1.457 meters upward. So and then let's say we found that one point at 2.5 meter here. So and then we need to calculate its alternate depth. Okay, first we need to compare the point given in the question, which is 2.5 meter here, is larger or lesser than the critical point. So we found that 2.5 meter here is greater than 0.971. So means that in the graph here, so we have the specific energy curve, and then this is the critical, which is the 0.971. And then if the location is 2.5, so we get the 2.5 here. Okay, so we have one. So I hope you could imagine. Now we have 2.5 here, so mean the location, the point is here. So and then we need to find what is the another point occur at this one. So another depth that give you the same amount of energy at this point. Okay, so what we need to do is we need to calculate the energy. So we know the velocity, the energy equation is E equal Y plus Q square over 2GY square. So we substitute the value of Y, which is 2.5 meter. Okay, so means that we substitute that, we found that the energy is 2.57. Okay, so and then this value is the same for the other alternate depth. So and then here you could imagine that one is occur at 2.5, means at subcritical region here. So means that another point or another point is actually occur at supercritical region. Okay, so means that what we need to do for the second calculation is we still use the same energy equation here. So what we need is, so we already calculate the value of energy here, 2.57. So we substitute this value into this equation. So this is the E. So now the unknown is the Y. So there are two Y here. So means that you need to, by hook or by crook, by using trial and error methods, so you need to calculate the value of Y. So and then the trick is very simple. So we have the curve here. So we know it is the critical. So the 2.5 meter is above the critical depth. So mean the another point is occur between this region. This is 0.971. So means that you need to try and error the value which is lower than 0.971. Okay, sometimes student make silly mistake, which is student try and error, do the trial and error method, and then the final answer is 2.5. So you will get same value of energy if you substitute 2.5 meter, because this is the point here. Okay, please do not make same mistake like this. So you need to know which region that you want to calculate, and then you could assume the value. So in this situation, the value must be between 0 and 0.971. So if we use try and error method, we found that it is, okay, so let's say we create an equation in Excel, and then we need to find what is the nearest answer there. So we found that to get 2.57, so the value of y is 0.467. So we get that the y is 0.467. Okay, so this is the idea of hydraulic jump, or the idea of this specific energy curve. So the idea is very simple. We found that from here, the energy is become lower and lower because the depth is become shallow and shallow. Okay, but at one point here, so we found that the energy is minimum, very minimum. Okay, and occur at certain depth. Okay, so and then after this, the energy will increase rapidly. Okay, so means that if we want to reflect this curve into a real situation, so this might be the simple idea. So let's say you have a water flow from left to right like this one, and then the energy is become reduced slower and become slower here. So and then the depth here is become shallow and shallower, and then at certain point here you will find that the velocity of the waterfall is rapidly increased. So and then this rapid velocity will give you increment of energy. So means that if you have a ship here, so if you have a ship here, you will find that at this region you still can go back, you can still turn back, okay, to prevent the accident. But however, after you reach the critical point, so means the energy is very high, the changes of energy is very high, and then you cannot do anything, so you will fall from this point. So this is the algorithm, or the idea of the critical and the critical point, and also the alternate point. Okay, and then the relation of that one, the supercritical, critical condition, and subcritical is actually about one phenomenon called the hydraulic jump. So in open channel flow, a supercritical flow can change quickly back to a subcritical flow by passing through a hydraulic jump. The upstream flow is fast and shallow. The downstream flow is slow and deep. The hydraulic jump is quite thick, ranging in length from 4 to 6 times the downstream depth. It is very important that such jump be located on specifically designed aprons. Otherwise, the channel bottom will be badly scored by the agitation. Jumps also mix fluid very effectively and have application to sewage and water treatment design. So the idea is very simple. If the water flow, let's say this is the bottom one, the bottom plane, and then the water is very shallow here, but it's flow at high energy. After certain time, when the energy become higher and higher, so means that the in simple words, this thickness cannot hold that energy. So what happened is energy will increase the volume and start to flow. Okay, so at this one, actually there is a flow back. So means that the flow actually cannot go through there, cannot flow forward, because there is the simple word is there is a traffic jam there. So what happened, they will have a reverse flow like this, and then it will increase the depth. So and then after the hydraulic jump occur, so means that the energy is released at this situation, so the depth of this one will back to normal. So it takes a certain distance here to from the hydraulic jump into the normal flow. Okay, so this is what we need to take care if we have an open channel, because sometimes the damage is very severe, so it could break the sewage drainage. Okay, so this is the idea of hydraulic jump. For example, we have a slope here, so we have a water from here. So this is very shallow. However, the water cannot go to the right easily. So what happened? They will have a vortex here, and then it will increase the level. So this is the value of fraud number. Let's say from 1 to 1.7, might be we have just a small increment here. So and then until 2.5, so there is some kind of weak jump. So the water is still flow like this one, and also just a few vortices occur. So and then for around 4.5, 2.5 to 4.5, so there is a lot of this one. So and then if you have until 9, so it's a steady jump. So steady jump means that the shape of the jump is quite predictable. It's stay at a certain height and so on. So and then more than 9.0, so it might be a very strong jump, means the height is quite predictable, but it comes with a severe wave, something like that. So this is what we call the hydraulic jump. So and then the application of this one is related to the construction of dam. So because in dam we need to have wear. So we learned about wear in fluid mechanics 1 to calculate the flow rate and so on. And then the application of wear is actually to use by turbine. So normally we will put certain turbine here, or we put a turbine here. So after the water hit the turbine, so we could get electricity from the turbine. So water need to be released to the river. So then to release the water, so we need to have some technology. So normally because to prevent the hydraulic jump. So and then type of wear here, okay, as we could see from the slide. So we have some kind of sharp crested wear here. So means that this is a very sharp. So the water will flow like this. So and then it will create a space here. So normally water could go flow this direction and also to this direction. And then at certain design, so we call it as a broad crested. So means that we just put a long path here for water, and then the water could go through here steadily before it's flowed down like this one. So and then this is just an extra notes. Okay, we will have this in our last tutorial, because sometimes for very special design of wear, for example for this one or for this one, it is advantage for us to calculate its own flow rate first. So the flow rate for sharp crested wear can be written as this one, and the value of 0.81 is actually the coefficient. So it can change in question, and it could change according to the validation of calculation and the real works. So and then for the broad crested wear, so the calculation of Q, the flow rate can be found like this one. Okay, so and then there is a lot of calculation depend on the question. I will show you in tutorial parts later on. So for example, for the value, the ratio of H and Y mean the width of wear, and also the thickness, the height of the wear. Okay, so and then it's depend on this equation. So I hope you could just print screen these notes and then make your own notes. After that, when we answer tutorial question, you could refer to these notes. Okay, so this is another equation or another flow rate for different type of wear. Okay, so this is the idea. So this is the full width rectangular. So you could use this idea. So and then if we have the design of wear like this, so this is the equation, and if the rectangular wear, so this is the equation. So I think in fluid mechanics 1 we already learned about these two type of wear. We have a triangular wear and rectangular wear. So if you still have your fluid mechanics 1 notes, you could see the discussion of rectangular and the triangular wear.